Before I get into a famous concrete example of a proof by contradiction, let me just reinforce. You're trying to prove a mathematical statement P, and if you're going to use proof by contradiction, you will start with the contrary, the contradiction of P, in other words, not P. From not P, you deduce something, call it Q, some other mathematical statement. So, if not P, then Q. Okay? But in reality, not Q is true. So you've got a contradiction of Q. So if not Q is true, then the left-hand side is false. So you've got not P. Okay? But not P is the same as P. So you've proved P. That's the essence of proving by contradiction. So I suppose before I get on to the actual example, you may ask a broader question. How do you know which proof method, which type of proof to use? Like, do you use, you look at a particular problem, and do you use proof by construction? Do you use proof by contradiction? Do you use proof by induction, or whatever? Well, like I said, theorem proving is an art. Okay, there may be guidelines, but anyway, they're not. This bigger, broader question is not discussed in this textbook, at least. Well, yeah, that's all I'll say. All right, let's pass on to a famous concrete example of a proof by contradiction. Now, it goes back to, and there's a story that goes with it, which is an interesting little story, so I'll give it to you. It goes back to the times of Pythagoras, the famous ancient Greek mathematician, logician, and Pythagoras was absolutely in love with numbers, integers particularly, and he thought numbers were the secret to understanding the universe. And in a sense he's right. I mean, modern mathematical physics, which is from its very label, is all about the application of mathematics to describing nature. Right? That's what it's all about. A lot of people think that if the universe is designed, if you're a deist, and I'm open to deism, I'm not saying it's true, but I'm not saying it's false either. So I'm agnostic about, well, I'm ignorant about whether it's true or false, but I'm open to it. And the suspicion is, and a lot of people think this, that if the universe has been designed, it was designed by an extremely competent mathematician. So the deity is a mathematical god, so to speak. So anyway, so Pythagoras loved numbers, and he discovered that the harmonious notes when you're making music, like the length of strings on a guitar, if they were in simple proportions, simple ratios like 2:1, 3:1, that kind of thing, then the notes produced were harmonious. They seemed to go well together when you made a chord. They weren't discordant. Okay, so that created a big impression on him. So he thought nature was about, could be reflected, modeled, like represented, understood, many ways of saying, by numbers, by integers. And so Pythagoras, also famous of course for discovering Pythagoras' theorem, which interestingly has been discovered, I read, independently by about at least five other cultures. Okay, so makes you wonder, about the famous question, the philosophy of mathematics. Are these theorems? Are they created? Are they sort of like an artist creating a painting, or are they, in a sense, discovered? Right? Like they're there, just waiting to be found by mathematicians. A lot of mathematicians feel that they are discovered. In some sense, these mathematical truths are out there, waiting to be discovered. Now, what does "there" mean? These are deep philosophical issues, right? There's a whole branch of philosophy on the philosophy of mathematics, and this is one of the big questions. Theorems, mathematical statements that seem to be true, are they creations of the human mind, like a painting, or are they discoveries? Are they saying something about the real world? Well, a lot of people feel they're saying something about the real world, and they're saying something about mathematics per se. There's a kind of mathematical reality somehow, and deep metaphysical questions. Interesting stuff if you're philosophically inclined. Okay, so Pythagoras discovered his famous theorem about right-angled triangles. So if the hypotenuse on your right-angled triangle, call that length C. So the other two sides, A and B, now you probably know Pythagoras' theorem. So the sum of the squares on the other two lengths, so A squared plus B squared, that number, that sum, is equal to the length squared of the hypotenuse, the sloping line. So you've got the base, the height. So A, that's B, that'll be C. So A squared plus B squared equals C squared. Well, then if the base and the height are both 1, so if A equals B equals 1, then the C squared will be 1 squared plus 1 squared. In other words, A squared plus B squared. That's 1 squared plus 1 squared is 2. Okay? So C squared is 2. And that means that C is the square root of 2. Okay? Now, once this was realized, that if you have a base of 1 and a height of 1 in a right-angled triangle, then the hypotenuse length, C, is square root of 2. And people started thinking about this. This group of followers that Pythagoras created. He was a brilliant mind and attracted followers. And they, I don't know the details, but they discovered that C, square root of 2 in other words, was not a number that could be expressed as one integer divided by another integer. So long as the integer that you divide by is not 0. It can't divide by 0. That creates problems. So this is puzzling and deeply disturbing to Pythagoras, because he thought everything was of the form integers, or the ratio, the proportion, A over B. A and B are integers. So that he thought that was the way the world was. But no, here's this square root of 2, which is not of that form. Now, numbers that are of the form, one integer divided by another integer, as long as the second integer is not 0. So, numbers that take the form of A over B, where A and B are integers, B is not 0, and assuming also that A and B have 0 common factors. They don't have any common factors. Like if you had a number like this, 4 over 6, well, divide through by the common factors. So you get numbers. You get two integers here that have no common factors at all, right? So they've been your ratio has been simplified down until there are just no more common factors between the upper number and the lower number. Okay? And now that kind of number that's been simplified, where the numerator and the denominator are both integers, non-zero, well, this one is non-zero integer, the b underneath. That kind of number is known as a rational number. Rational sort of makes sense, right, according to Pythagoras. So they were called rational numbers. Right? Now, it works out that square root of 2 is not a rational number, and we'll prove that, and we'll prove it by contradiction. Okay? So it's a famous proof. Now, this proof that the Pythagoreans, I think, showed using by contradiction, because there was another Greek around that time, famous Greek, Euclid, who used a similar argument, by contradiction, to show that there is no maximum prime number. In other words, the primes just go on forever.